Welcome back. In this video, we are going to explore some applications of exponential functions. And exponential functions are used in both growth and decay type of problems. Now, before I get going on this, you will want your calculator for this, and you will want to be able to know how to use exponents and apply exponents. And I can show you this on the TI graphing calculator. Here's an example of a growth function. The concentration of carbon dioxide in parts per million in the air is approximated by the function f of x equals 266 times 1.001 all raised to the x power, where x is the number of years since 1750. Use this function on your calculator to approximate the concentration of carbon dioxide in parts per million for these years. So let's take a look at the year 1900. So that is our x. 1900, well, it appears to be our x. However, x is the number of years since 1750. So 1900 minus 1750 is 150. So in this example, our x is 150. It's 150 years after 1750. So we are going to work with f of 150 equals 266 times 1.001 all raised to the 150th power. So be careful here. Watch your order of operations. PEMDAS tells us we want to do our exponents before we multiply. So we want to apply the exponent first, so we've got to impose the 150 on the 1.001. Then we multiply by 266. Well, the good news here is that your calculator will do the work for you. So we can go right to our graphing calculator and input our information. 266 times 1.001 all raised, so we'll use the caret key here, all raised to the 150th power. And we get 309. So our final answer then is approximately 309 parts per million. And they're asking us to do this again for 1950. Well, hopefully we see right away that that's 200 years afterwards. So now we would just input f of 200. 266 times 1.001 raised now to the 200th power. And we can go to our calculator. And second entry. And use my same entry. And now I'll just put 200 in. That was going to be easy if I didn't go over my caret. So there we go, to the 200th power, and hit enter, and I get 324.86, or about 325 parts per million. Let's take a look at a decay problem. Decay problem. Here we have the atmospheric pressure in millibars at a given altitude x in meters, so the altitude height is in meters, can be approximated by the function f of x equals 1038 times 1.000134 all raised to the negative x power. And this function holds for values of x between 0 and 10,000. So if 0 is probably ground level and 10,000, well, 10,000 meters high, That's pretty high. That's about 6 miles in the air. So note, because the base is greater than 1 and the coefficient x in the exponent is negative, the function values decrease as x increases. Thus, as altitude increases, so as x rises, our f of x, our atmospheric pressure, is going to decrease. So our first question here is to calculate the pressure at ground level. So ground level, we're going to look at that as a height equals 0. So that's our x. So f of 0 equals 1,038, 1.000134 raised all to the negative 0 power. And isn't anything to the 0 power 1? So f of 0 equals 1,038 times 1, because this is now collapses to 1, and we will get 1,038. So that was kind of an easy one. We didn't even need our calculator for that. So let's take a look at the pressure at 5,000 feet using our function. F of 5,000 equals 1,038 times 1.000134, all raised to the negative 5,000 power. So remember, this is a negative exponent, so this is a fraction. This really is 1,038 all divided by 1.000134 raised to the 5,000th power. Well, we're not going to have to put that into our calculator that way, but that's what's going on. But we can just go ahead and input this into our calculator, same way we did before. So we have a new function, 1,038 times 1.000134, all raised to the negative, and I'm going to use this key here, to the negative 5,000. And I get 531. So our final answer here, f of 5,000 equals about 531 millibars. And that makes sense. As we rose from ground level, our pressure went from 1,038 to 5,000 feet. It decreased to 531. So as our altitude increased to 5,000, our atmospheric pressure decreased. So there's a couple good examples of application of exponential functions, one for growth and one for decay, and we will see you in class.